Yeah, this video shows the Hydra conference is not only the concurrency conference, but it's a distributed computing conference too. Ivan, Aleksey, welcome to Hydra 2021. How is it going?
Hello, hello. Yeah,
Hi.
Wonderful.
Yeah, it's good.
Yeah, I tried to make a short introduction for both of you, but my understanding is that Ivan prepared something more. Ivan.
Yeah. Of course, I bet everybody knows Aleksey Shipilev, at least on the Roost scene. To be honest, my personal journey into the concurrent world has been started from Alex, one of the talk. Out of his talk about 10 years ago, there was a talk about the fork join pool that was a brand new feature in Java 7, if I'm not mistaken. And it was like I was young and naive, and I went to the talk, and that was like magic because I really didn't understand anything. So that was like a brand new world that was really next to me, and that was really enjoyment to explore and learn more and more. And for that journey, I really have to say thank you, Aleksey Shipilev, and all his work. And I grew up myself and grow up and see how he improves Java and benchmarking and concurrency and now garbage collection. So thank you, Alex, and I hope today we will have a wonderful workshop about very specific but really interesting tool. How can we improve, verify the Java memory model?
So my understanding is if you call Aleksey Alex, he should call you Ivan. I think it's
okay.
good way to answer something for this. Thank you, Vanya, for the introduction. Yosha, how is it going?
Yeah, it's good. It's quite hot here, so if I would start to sweat a lot, it's not because I'm tanking this workshop, but maybe it is, but because it is way too hot here. Yeah.
Okay, so I have a small question to you before the very beginning of the talk. Who is Reshetnev or Reshetnev on your T-shirt?
Yeah, my parents work in this interesting company, I guess, which is it's called Information Satellite Systems, which do basically satellites. And one of the founders of that facility is academic Reshetnev, who is basically one of the left hand or right hand of Korolev himself. Yeah. And so this is kind of the T-shirt that is homage to that organization. Yeah.
Okay, kind of Alaverdi. Okay, Vanya, do you have some more questions to Aleksey before we start?
Well, I just wanted to ask why are we here? So why one should care about JCStress and for whom you would say this workshop will be useful?
Oh yes. Okay. JCStress is mostly about testing JVMs. It's useful to do empirical testing of the higher level code, but in this workshop, we would mostly look at the JCStress itself a little bit, but mostly we'll be talking about the examples that show different things in Java memory model, because JCStress is mostly for verifying Java memory model. It was conceived as the tool for verifying Java memory model compatibilities in JVM. So naturally, you would see things in JMM. For users who would not use JCStress in their day-to-day life, I think this workshop is still useful to understand JMM better. Because you can do all these sorts of abstract things about JMM, about the abstract reasoning, the proofs, etc., and there is a little bit another experience to actually see something happen before your eyes. Yeah.
Yeah, that's a nice one. So probably we'll understand that freeze conception for final fields.
Oh, maybe.
Okay.
Okay, we're close to start, correct?
Yep. Ready.
Okay, ladies and gentlemen, JVM expert, benchmark inside, Mr. Aleksey Shipilev tonight at Hydra 2021.
Yeah, hi. So this is a workshop, but I have both slides in terminal and ID, and I will jump between them. So for the slides, let's set a few expectations here. What this workshop, how it's planned. We will be having two parts. The first part would be more basic. We will be looking at what JCStress is, how does it look, and look at the basic JMM samples there. Then we will have a short coffee break, and then we will have the advanced bits, which will talk more about how does JCStress achieves what it achieves, and why would you probably not do the same thing from scratch all over again. And we will be talking about more advanced JMM examples there. And then after that part is over and we have the discussion zone there, we can discuss more intricate stuff like future work, discussions, etc. If by some miracle we will have time in first two parts, we would also see the real JDK and JVM bugs that JCStress discovered. Those kind of gory details that are quite extreme for this workshop. Okay. Most of the code that we would be doing here is available as runnable JCStress samples in the JCStress workspace. So if you just Google JCStress, it will point you to the GitHub repository for JCStress. You can check it out. You can build it with JDK 11, and then it will produce the runnable jars that you can then run. I will give you a second to actually look at this URL if you want to type it in. Even though this is a workshop, you're not actually required to run the samples because most of those samples require a little bit of meditation around them. I will do some narrative around them, but probably it is from my own experience that it's useful to actually take your time and work through these examples in the relative peace of your study room. Okay, so involvement. This is what I'm talking about. You could run samples that I show you in this workshop. You're not required to do so. You can just see and listen and note the interesting cases and behaviors. And if you have specific questions about those behaviors, you can ask them in the Telegram chat. And Ivan and me would discuss it at the convenient points, and I will either do something with samples or refer to the other samples that come later. Okay. Let's start from the basic bits. In JCStress basics, a bit of the historical context. JCStress basically started around JDK 8 development time when I suddenly realized that there are hardly any regular concurrency tests that verify and ask questions about JMM conformance. I was trying to contribute some of the tests to JCK because JMM is described in chapter 17, so you would think that the tests that test JMM would be in JCK. But the problem with the conformance tests is that they have a very elevated standard for their pass-fail ratio, etc. Most of the concurrency tests are intrinsically probabilistic, so committing them in GCK is kind of hit and miss manner is probably not that good. And JVMs are notoriously hard to test because they are provided for many platforms. Even within one platform, there are many compilers. There are many compilation and runtime modes that you can try. And test behavior frequently depends on the runtime profile, etc. This is why I started JCStress as the exploratory project, but then it kind of snowballed into what it is right now. A little bit of the scoping. JCStress is a Java testing framework. It targets low-level JVM work, but it also touches hardware. We have seen that porters were running JCStress quite a bit for their ports to verify whether their JVM implementations work, but also if their experimental hardware works. Because if you fail JCStress there, it's a high red flag that something is probably wrong in your hardware. And we have seen examples when it actually found silicon bugs in hardware. It is empirical. It's not model checking. It does not trust that lower layers are sane. It does not trust that JVM is sane, OS or hardware. That's indeed the target for the testing in this framework. It's combinatorial. It runs many configurations of the same test, seeing what is available in your hardware machine, or etc. And it's experimental. It's usually written there in description in the large letters. And this experimental status gives us the ability to actually experiment with the new techniques for testing stuff, even if that breaks testing API every so often. Once again, not model checking. If you want model checking, go to the link check workshop. It was held on the first day of the conference. It's available in recording. We would not be talking about model checking. We would be only talking about empirical testing here. Some prior art. If you are tasked with the question of answering the question whether JVM supports JMM in a compatible manner, what can you do? As I said, JCK is there. It tests some clauses from chapter 17, but it does not accept the probabilistic tests like JCStress. And it's really, the chapter is really written in such a way that it's really hard to test if you stick to the normative text of that chapter. There is a JSR 166 TCK. JSR 166 is Java util concurrent. There is a TCK written for it by Doug Lee and other implementers. It's mostly tests Java util concurrent. It sometimes finds the bugs in JMM support after you realize that some of the tests is broken and you do not understand why. And there is the Litmus DUI test, which is developed by Peter Sewell's group. It's a really, really, really good harness to experiment with what hardware does. Those people in that lab actually did models for x86-64, Power, ARM, the formal models, and they verified those formal models with this kinds of tools. But it's mostly geared towards understanding hardware, not understanding compilers or runtimes or language memory models. Early attempts in concurrency testings usually fail on this simple thing. Concurrency bugs are data race or race condition bugs. So if you want to test for it, you need to create a controllable race condition. And you have to have it large enough so that the threads eventually meet under this racy condition. And you also want to have it small enough so you can still trust the results, because if you have the unbounded race, the results that you have from this kind of collision between threads are not reliable. You cannot tell anything from them. And you want to have this infrastructure fast enough, because since the test is probabilistic, the more samples you get, you would think that the more probability it is that you will see at least one of the interesting cases that are probably low probability ones. Unfortunately, naive tests do not check all these boxes. If you ask people how would you test this kind of concurrency thing, they would say, well, let's say we want to test whether the volatile increment is atomic. What would you do? You would have a volatile in V. You will have two threads, which are, thanks to Java 8's lambdas, can be just handed the lambda, which increments V. You start the threads, you wait for them to join, and you just assert that 2 is there in the variable. This test, while it kind of works, it's also problematic because the collision window between these two threads is very, very narrow. By the time one thread starts, the other thread is probably already finished. They rarely ever meet. So when you look at that, you say, well, let's solve that problem. We will have something like countdown latch and say we will start the threads, we'll make them wait on that countdown latch, and when both are there, threads are there, they unpark and you do v++. It's better than the previous example, but it's still problematic. Threads very rarely meet, and synchronization costs dominate here. And here comes the idea for the JCStress. When you say, look, we don't know from the beginning what should be the infrastructure to actually test this kind of stuff. So what do? We abstract it away, right? We say, let's ask user to write the test for us and let us then decide how to run it. So in JCStress, if you want to do this volatile increment test, you write it like this. You say, this is my test. This test carries the state. This state is depicted by that variable v. And I have two actors, actor 1 and actor 2, which by the API spec, they run once against every state, and they store, they do something about the state and store the result, third result in the provided storage. So hardness itself just says, I have a large array of single-use state-bearing objects. Actor accesses them one by one, save the observation in the provided storage and test infrastructure, then counts the observations there. All right, and in the end, we would have something like this. We'll have the history of the things that happened. In this example, for example, the atomicity failure in v++ means that both threads have incremented and both threads had observed 1. So the collision case is that interesting case 1, 1, which out of the 500 million of samples is 50 million of samples there, about 10% of this thing. It's a very basic test for any empirical concurrency testing tool that you can get. Volatiles, the natural collision window is very large in this test. So it's really a measure of how well a harness is able to exploit this kind of thing, right? Because if you cannot do something basic like this, you would not be able to catch a very rare things there. All right, let's go for some JCStress examples to go very quickly through the API, so you would understand what you would see in the next talk. If you are reading for those who would read the slides offline, this is the examples that we will be doing there. And now we are switching to JCStress. And we will start from the very basic, oh, come on. All right, of course. We'll start from the same thing, right? Volatile increment, I had pre-increment, now it's post-increment, whatever. So what do? We say we increment something, right? And we store the result of that pre-increment there. How does the JCStress knows which actors to run? There is the simple annotation which marks the method that threads are running. So each actor would be run by each thread, right? How do we then tell the harness what to look for? We have the annotations which are conveniently called outcome, which says, if you see 1 and 1, then know that this is acceptable state, and it's also interesting. Interesting means that it will be printed specifically in the JCStress logging. It's useful when you follow up on the interesting results. There is a little descriptions that you can get to users asking, telling them what they actually see here. So in this case, right, we have like 3 possible outcomes: 1 and 1, 1 and 2, 2 and 1. The last 2 are kind of obvious, right? The first thread runs, then the other thread runs, and you have have no problems. If you have 1, 1, that means you have atomicity failure, right? So we can run it. I have the 1 wire here, right? Yes, terminal. JCStress initial is this. Whoa. Really? demo gods are against me right now. Oh, of course. Sorry, guys. Of course, documentation is outdated. You have to do underscore here. Because the class is API simple. No. Oh, come on. Don't buy me. Yeah. If it doesn't do anything, that means it does something. All right. So it runs many configurations, and in the end, we see the results across all configurations. And this is the real results. It says, this is the field V, and we have the atomicity failure 1 and 1 right there, right? We do not expect that atomicity failure there is wrong particularly. We know that that's acceptable. We just want to see this as the interesting example there. Okay. All right. And now we go to the JMM basics. I was talking in the introductions that we would be doing mostly the JMM kind of examples here because that's what JCStress is good for. But before we do that, we have to do some sort of attitude adjustment here. All programmers intuitively understand this thing about specification and implementation. And it's useful to think about JMM in the same terms. The good spec, if you ever specified methods, you want it to be specified in just the right level. If you under-specify the API, you can do, the methods can do whatever they please, or the language runtime can do whatever it please, and it's not useful because you cannot rely on any semantics of these methods. If you over-specify that, implementation choices are limited or downright impossible to do. So JMM is the thing that kind of tries to answer the very basic thing about the behavior of the language. And the language behavior in just about every programming language spec is described by the behavior of this abstract machine that runs the target, this programming language. And the part of how the storage behaves in this programming language, how the fields behave, etc. What results can you get from reading the field? That's what the Java memory model governs. The very important attitude adjustment here is that if you have the real result that is indistinguishable from the results that abstract machine produces in some of the executions, nobody cares how that result was achieved. So it's, for example, if you have like two local variables, x and y, and you sum them up and return them, you can just compile it to returning like the precompiled result there. No variables are there anymore, no addition there anymore, because that result is the result of the abstract machine there. Conversely, if you do something about volatile x, for instance, right, and you do x1, x2, and return x, the implementations are allowed to compile this to just returning 2, even though you might think that volatile is something that prevents optimizations, for instance. No, in this case, implementation could reasonably argue that this is the practical result, this is the theoretical result of the abstract machine execution, and therefore it's fine. Therefore, this optimization is allowed. In practice, many analyses are hard, especially global analysis, to do effectively in compilers, especially in JIT compilers. But still, the same kind of attitude adjustments fits. You should only care what abstract machine rules tell you, not what actual implementations do. And here's the problem with JMM. If you ever try to learn JMM, you say to yourself, oh, okay, give me 5 minutes, I will just read up this part of JLS. And the entire Java language spec is actually written in a very human readable language, except chapter 17 and the part that when you do things about method call order, etc. There you see something like an execution is described by tuple, which has a program set of action orders, given a right, blah, blah, blah. Well-formed executions, there exists. And it's really kind of looks like an alien thing in the JLS. So yeah, so people are generally displeased with that. And So my argument for this talk would be that you don't actually need this stuff to write correct programs if you follow simple rules, or you have like the phenomenological understanding of what can be and cannot be there. Of course, if you talk to the JMM guys like me, they said, hold on, we will just describe very, very easily what JMM is. JMM says there are executions. Executions are the union of orders, of action orders and consistency rules. And here I see Ivan is already face-palming there because, yeah, you actually do this blank face every time you read this chapter. There are like actions which are defined as writes and reads, locking, unlocking. There are orders, happens before order, program order, synchronization order. There are consistency rules like PO, SO, SO, PO consistency. And there are rules over these orders which describe which executions are fine or not, etc., etc. And in the end, you arrive to this. You just say, I read this chapter like 15 times and I still have no idea what it said in that chapter. And of course, it's not very good. So let me give you a one-slide high-level overview why Java memory model is there and how it's technically can be used to prove things. So here's the thing. If you have the original program, let's say there is a program in the common notation, something on the top is something that is given. This is the variable a, it's initialized to 0. And there are two columns which are colloquially describing the threads. So first thread does A1 and R1 equals A, and the other thread does A2, right? So JMM says, if we give this program to the abstract machine, what would be the results of that abstract machine? Those results are governed by executions. We can actually map what program can do to the actions, construct all the different executions that could happen in that abstract machine. And from there, we can say that R1, the local variable there in the first thread, can take either 1 or 2 as the possible value there. This is like the top one is like the theoretical thing there. The implementations could say, look, we know this program on the left. We can just store 1 to A and say that R1 is 1 unconditionally. And we will always say that R1 is 1. And this whole thing is perfectly fine until, while my implementation produces some subsets of results that are allowed by the theoretical derivation there. All right? So takeaways from here, implementations are allowed to generate a subset of allowed outcomes, not all of them. You can study JSR 133 cookbook for compiler writers. You can study what implementations do, but take it with a grain of salt. My favorite reduction ad absurdum argument is that suppose your implementation does global interpreter lock and you never see any of this sort of racy behavior at all in your program. Does that mean that your language is that strong? No, that's an implementation thing there. And the second takeaway that's useful for us for the empirical testing is that the universe is under no obligation to show you all possible outcomes that can be produced in the implementation or the spec. If you don't see something that reproduces, it does not mean it's not possible. Although biasist would probably tell us that if you don't see something happening over and over and over again in an experiment, it's probably the weak evidence of impossibility, but it's not really a strong evidence there. All right. Anything about JMM? There used to be a JMM update JEP. JEP is a Java enhancement process for non-Java peeps there. It was targeted to do a few things. It was targeted to do improved formalization, JVM coverage, meeting the specification implementation coverage improved. In scope, covering some dark corners there. Be compatible with C++ and C++11. Sorry, with C11 and C++11, which introduced the atomics and memory model, along with weaker forms of synchronizations, which Java also wanted to have, provide implementation guidance, etc., for one terrible conclusion that JEP is basically stalled. But instead, we've got a library thing there, which kind of does the most significant part of that job. It introduces the weaker forms of synchronization. Right now, well, not right now. In Java 8, you have like plain fields and volatiles is like all or nothing. Var handles provide you with opaque mode, with acquire and release mode, and the volatile mode. And the samples would show what those modes are. And these modes are interesting because you can loosely define what they mean without going to the JMM specifics. You can actually have the intuition about these modes without teaching people hard stuff about JLS 17. All right. So if you go for the overview, we will be talking in our samples about the properties that are there in the header row, whether it's defined, atomic, coherent, there's causality, there's consensus, and resilience. We will talk about each of those things later. But this kind of gives you the perspective that before in Java 8, you kind of have plain things that only defined, and volatile things that kind of do everything else. And you, in Java 9 and later, you have these var handle accesses that are useful there. And there's also a final, which is not fitting in this nomenclature very precisely, but it will be important going forward anyway. All right, so we will go and look through these samples. All right, it's the basic samples there. But before we go there, we have to do some definitions. The first sample would deal with the data races. It's important to define this. Data races are usually defined this way. They say, look, let's first define what conflict is. And the conflict is when two threads are accessing the same variable and at least one of those threads is writer. Two immediate things follow from this. If you do only readers on some variable, it's not a conflict. That's fine. And that you also could have an interesting write-write conflicts when nobody reads the value yet, but you have the writer there. So data race is the conflict that's not ordered by synchronization. Right? It's the key problem in the low-level concurrency that you have to deal with. Up to the point that Java Memory Model and other languages model adopted so-called SCDRF, which says that if you don't have any data races in your program, that all the behaviors of the program is as if they are sequentially consistent, which is a very strong property there. And also, I want to give you the definition of the race condition. The race condition is when system behavior is dependent on the timing of the events. You can have the system which does not have data races, but still full of race conditions. And race conditions are not necessarily bad, because they only become bad and bugs when some of the behaviors that arise from those race conditions are undesirable. But otherwise, it's the key to performance to allow this kind of things there. Okay. And let's look at JCStress. Ivan, I would ask you a question soon, so pay attention.
Yeah, I'm ready.
All right. So suppose you have this test. You have the object O. You have the writer that writes the object, and you have the reader that reads it. It reads it into a local variable, checks it for null. If it's null, it stores null as the result. This is actually the reference field. If it's not null, we pick up the class from there, or if we, for some reason, get the null pointer exception from here, we will store that NP. So what would you think be there in L result for the practical cases?
Yeah, interesting. So for sure, the exception might be accessible result. Of course, null. Of course, the O. And of course, the object class itself.
Yeah, I will run it while talking.
Okay.
All right.
Okay. But but I can't think of anything else, to be honest.
All right.
So
you basically said that all three
fine.
are possible, right?
Yeah, all three are fine for me. Yeah.
Yeah. Okay. There are no interesting cases. Sorry. So it doesn't print anything. So I have to run it with the verbose. option there. Okay. If you run it on just about every platform that is out there, you would see this basically. You'll see these two outcomes.
Oh, no null point exception.
No null pointer exception. Notice that we have read this thing into the local variable, and we null check it here.
Right. Yeah, and it can't be. It doesn't matter if we concurrent write to yeah, because we use that pattern to write to the local variable. Yeah, I see.
Good. Yeah. Very good. And this is one of the major takeaways from Java. In Java, unlike, say, C and C++, where data race is undefined behavior, in Java, behavior under data races is more or less defined. So if you do something, if you read something in the local variable, null check it, you can be guaranteed that it's not null anymore. In C and C++, this kind of thing is dangerous. We've actually seen compilers that broke this code, and they were within their rights by the C standard there. Right? This is kind of the property that is taken for granted by Java developers, but it's actually a very strong guarantee in the language itself. There is the JMM argument why other examples are not possible there, but this workshop is too short to actually go into there. If you are reading it after the talk, there is the backup section in the slides. You can just scroll there, and there's the argument there. Other takeaways. So data race behavior is still deterministic. Weird stuff still happens, but it's kind of understandable there. In fact, the fact that Java is more or less fine with data races is something that allows JCStress to even exist, because JCStress gives you does run tests under the data races. If that behavior was completely undefined, you could just crash the VM at that point if that was a legitimate behavior. But no, in Java it isn't. You can do a data race and not crash VM. In fact, no valid Java program should be able to crash the VM. And also, memory model-wise, there is difference between these two kind of examples, right? When you read something from the heap twice, or when you do something in the local variable. On the right, you can be guaranteed that what you read from the field is the same value. So x1 and x2 are the same thing on every path there. It's also a very strong guarantee by the Java language. So yeah, this is the first column. It's defined. Even the plain accesses are very well defined, even if those accesses are under races. Regardless of the mode, it's kind of the overarching property of the Java programs. All right, access atomicity. Access atomicity is something also taken for granted by most of the people. So it says something like this. Suppose you have the variable t and initialize it with the variable with the value v1, and we have other thread that writes v2 there. So the question is, what can we read in the other thread when we read from that t? It's kind of expected that you can read only v1 or v2, right? We would expect that's true. Is it though, Ivan?
No, I think, because it's not volatile, so we can see all the previous results of the t, so including null, I think.
Yeah. Well, it's an interesting observation, right? You can see null. If not, if you read JCStress example API, it will say that whatever happened in the initial initializations would be seen by both actors. So v1 would be seen there. You would not see this kind of weird racy thing there. You would only see the race that is between the actors there. So null is not really possible. Is it possible for some other type, not maybe reference?
Interesting. Yeah, you're talking about partitional right? Something like if it's not atomic operation, like a long, we can see something weird because we have written only half of the data to the variable.
So if you do this kind of spoilers. Yeah, so if you do this kind of tests, right, we have long V.
Yeah, I'm sorry, Alex, and can I interrupt just a bit? Can you switch on your uplight? Because of the camera, seems like it reduced the FPS because of the lack of the.
Okay, just a sec. Oh no. Okay, let me do this. Is that better? No, that's worse. Is that better?
Yeah, how do you say? But yeah, I think we're fine.
Yeah. So let's run that thing here. Longs. Right. Here's the test. It says we write this long, which has all the bits set, and we try to read it back. So we would think that maybe something other is possible there, but it's not. Sorry, once again, I forgot V because it's not an interesting test case there. And on my machine, you would only see -1, which is basically the same thing here, right? To complement, or 0, right? But if you go and say, ask for the 32-bit machine, then you will suddenly realize that longs is 64-bit long, pun intended. So that would mean the VM would have to probably read and write that long in 2 pieces. And we will probably see those 2 pieces as interesting cases here, right? So what do we do to avoid this effect?
We use volatile, I think.
Yeah, we use volatile. Yes, there is a test case that tests volatile longs. You have to believe me that if I run it on the same machine, it would not produce this interesting results. And you might think that this is something of the problem of the past, because we have 64-bit machines. And so everything is atomic, access atomic there. But then you will go and run into, say, Valhalla. And in Valhalla, you will see the tests like this. When you have a primitive class, it's red because my baseline JDK is not Valhalla enabled. When you can say, look, this is a primitive class with 2 long fields, and that value class would be inlined here as 2 fields. So if I write that value and read that value, at that point, my 64-bit VM is in this, again, in this weird condition when it has to read 128 bits from memory atomically, all in one sitting, but it can't because there is not such operation, so it has to read component by component, and you will see the same kind of atomicity failure there. Yeah. So this thing would probably resurface as value types would come in. Of course, as with volatile longs, you can turn this thing into the volatile thing like this, and then your that conditions would be forbidden. But how would a runtime do that then? In current Valhalla prototype, if you do this kind of thing on the declaration side, it will say, well, we cannot flatten the fields anymore. We cannot inline the components of this primitive class value in the class because we would not be able to do the reads and writes atomically, right? So you will see this thing resurface in the future. All right. Yeah, so takeaways from here. Most built-in types are access atomic. Most of them are naturally aligned unless 32-bit VMs are present. When you will have larger primitive types, access atomicity will probably break again by default. So do not unlearn this rule just yet. You will see it going into the future. If you do unnatural access like unsafe or byte buffers, there are examples in JCStress that tells that the compound operations are also not access atomic because the underlying implementations do this component by component reads and writes. All right. So atomicity, this is the second column there. Plane is kind of atomic, but not axis atomic, but not really. So longs and doubles are specified as not atomic, even though implementations could be stronger. All other access modes are actually providing you with the this more stronger property. We already seen that putting volatile restores this, but also every other weaker form of synchronizations also restores this access atomicity thing. All right. Now, coherence. Coherence is an interesting thing. Coherence is defined that the writes to the single memory location appear to be in the total order consistent with the program order. Yeah. Most hardware actually gives this for free because most hardware is cache coherent. It's basically provided by the coherency protocols. Notice that concurrency problems come when you have several locations updated at the same time, heavy air quotes, where the juxtapositions between those updates gives you interesting behaviors. But if you look at the single memory locations, your hardware usually maintains the single order of updates there, unless you have optimizing compilers, which give up on this property because they usually don't track the order of reads. They can reorder reads unless there is something that prevents them from doing so, like memory barriers or synchronization operations or something like this. All right. So we're going to switch to JCStress right now, and we'll talk about coherence a little bit.
Alex, and until we jump the next topic, we have a few questions. Would you like to answer them now, or probably at the end?
Yeah, let's push through this. All right, no, let's do this. Yeah, let's do the questions about the races and atomic accesses. Yes. Go.
Okay, so the quick question about from Mark: if we don't use local variable, so the null pointer exception would be accessible,
yes,
right? In your previous example.
Yeah, this actually goes towards the coherence example that I'm about to show you. Yeah.
Okay. So we'll see it in the future. So, and another question from Vasily Galkin: Are all those guarantees for graceful races specific for Java language or for a JVM platform and all JVM basis languages?
It is based in the Java language specification. The Java memory model is specified there, but this is something about the awkward thing. JVM specification does not say about memory model, so it's kind of implied that JVM follows the Java memory model. So you can probably argue that it is true for every Java language out there, provided the implementations of these languages do not do some weird stuff on their own.
Okay, so we kind of in Kotlin Scala we can see all that stuff.
Yeah,
right.
I would argue that's a bug if they behave otherwise.
Okay, I see.
All right.
Okay, so we thanks. That's all the questions so far. So we're ready to see for the coherence example.
Yeah, coherence. So coherence is basically this. Suppose we have the whole the class holder here, which has integer a, right? And we have two holders reachable through the different pointers here, references. Sorry, right? It's the same holder there, and we write a to one of these instances, and then we want to read a through either of these references there. It's kind of a contrived example because I would rather do a plain field A and just read from it twice, but I need to confuse my optimizer not to call as these reads to make them distinct, so I have to do this trick of accessing it through two different references. But the question is, what outcomes are plausible here?
Could you scroll up just a bit? So we have a holder, we have two different ends, and trap. We have two holders. Let's say trap O.
Yeah, ignore this. This is to confuse optimizer. Yeah.
Okay. So so with trap we completely ignore.
Yeah. Let me just run it while you're thinking about it.
Yeah, sure.
This 0.5, right? So obviously, right? If we say, look, Coherence says that there is the single order of writes, right, observed by every application. So if we do store 1 here, what can we see? We can see first 1 and 1, right? When we read one thread completely, we can see 0, 0 because we do this the vice versa. We can see 0 and 1. Right, because we have seen read A once, then the write happened, then we see the read again. Now the question is whether we can see 1 and 0, whether we can see 1 here and 0 here.
Yeah, I think yes, but that's very unlikely. But I think yes.
Yeah.
But we didn't see on your machine.
Yes, we didn't see the same machine because it's the same one. It's the other subtest, I think. And it's opaque. And here's the same read. There are several subtests in this. This is the same read subtest. Here's the same read subtest. And here we see 0 and 1.
The interesting one.
Yeah. And this thing is mostly compiler induced because it's the compiler who actually reordered these two reads. If we expose these reads to the machine in the hardware order, it would be fine because hardware provides us with the concurrency. So this is why there is this test say a same opaque read, which does the same thing, but it reads with opaque, which does not do any sort of other memory effects at all. It just says whatever order it is in the program, issue these reads in the same order to the target hardware. And this is why in the subtest that's called same opaque read here, we don't see this thing because it now violates the hardware provided coherence.
So opaque means only do not reorder this instruction with any other.
Mostly, yes. Here's the useful table again. This is the third column, coherence. Plain reads are not coherent under JMM rules. If you do anything else, if you do opaque, they are coherent at that point again. Right. Right. Causality. Causality is an interesting property. It basically says that if something happened, then something else happened too. If A happened, then B happened. It is by far the most basic guarantee made by most memory model. The problem with learning memory models is accepting that this is, by and large, the only guiding principle in defining memory models. You don't usually have total orders unless there are specific things that to enforce it. You mostly have this kind of if A happened, then B happened. And it's also the cornerstone of most, if not all, distributed consistency models. You can see it in different forms: logical times, time codes, whatever, things like that. And we will go to the JCStress and see one of the causality examples there. Okay, so suppose we have this example. We have X and Y. We have one thread that writes 1 and 1 to X and Y, and the other guy reads Y and then reads X. So what outcomes are plausible here? Again, while you are thinking about it, let me run it. Oh. Well, once again, 1 and 1 are plausible, and 0 and 0 are plausible, right? Because this is just the one thread or the other running. Again, it is plausible to see 0 and 1, right? 0 and 1, because it's interleaving of the threads. First this write happens, then this read happens, reads 0. Then this write happens, but there is no read to read from it, and then this read happens, so on 0. The question is whether you can see this.
I think yes, with the same idea as before, right? Because it's a plain text, we can plain variable, we can see all the previous values.
Yeah, and we can clearly see this. Or even on x86-64, we see 1 and 0, right? How do we prevent this from happening?
I think we can use happens before edge somewhere on the Y, I think. Volatile.
On the Y, yes. So we can do something like this, right?
Yeah, that's one.
Yeah, volatile part. Yes, and here we say, basically, if I've seen 1 here, we say Y happened. That implies I have to see that x equals y also happened. Right? This is what causality means here. By the way, see that we don't see the forbidden the result anymore. It's forbidden right now, right? And you might think this is the compiler induced, but if you run the test with opaques again, so you just do the same kind of thing. You don't do y volatile, but you do opaque writes, and you do opaque reads, you still see, I think you will still see it. So if I've just allowed the optimizer to kind of reorder these two things, right? This result would be obvious, right? But if I issue that into to hardware with this thing, on x86-64, I would see 0 there. But if I go and do the same thing to other, like ARM64, and this is this, sure. Not here, not Java. Come on. The opaque reads, writes and reads are now introduced to the hardware in the same order that's written in the test. So no compiler is doing any weird things for us, right? But if you run it, we will see that it's the hardware that breaks this thing for us, right?
Oh.
Yeah, this is the hallmark of the weakly ordered machines like ARM64. You don't see this on the strongly ordered machines like x86-64. You go to ARM, and there you have it. From here, you have a simple rule for GMM. It's called safe publication. It is as if it commits to memory, but not quite. It's for this particular allocation in the memory. If you write to, say, to volatile variable, it releases everything that was written before it, so that if the reader reads another thread from the same volatile variable and it reads the same value, the value that was written by the first thread, it would also observe all the things that the first thread had written. That's called safe publication because I've safely published everything from the first thread to the other thread. All right? It's the major rule that you can get from the Java memory model. You don't really have to go to the JMM formalism to actually use it. You just identify acquires and releases in your programs. Make sure that every cross-thread communications has acquires and releases in the right order. And that's it. and you will have like 95% of all your concurrency problems solved if you just apply this rule. All right. So causality. This is the fourth column here. Plain reads are not do not provide causality. We have seen that opaque reads do not provide causality on ARM64 example. It's the hardware-induced thing there. It's not compiler-induced thing. Acquire and release mode, as you can see from its name, it kind of provides you with this guarantee that you will have the acquiring reads and releasing stores there, and sequential consistency as well. All right. Consensus. Consensus is an interesting property, very strong one. It is a momentary agreement between the threads about the program state. There are different powers of consensus. If you ever read the Art of Multiprocessor Programming textbook, it will have the whole chapter on discussing what kinds of consensus there are, what are the relative power of synchronization primitives, what are those consensus numbers of those concurrency primitives, etc. And consensus is mostly about multiple variables at once. If we only had a single variable, the coherence would probably be enough by definition. But this is about the several things there. And for that, we have the example like this. It's called Decker test. So again, we have two fields, x and y. The first thread says x equals y, x equals 1, and it reads from y. And the other thread does the same thing, vice versa. Stores to y, writes to x. So what would be the plausible results for R1 and R2 here?
Oh, yeah, I think, 1, 1 for sure, 0, for sure.
Yes.
Well, any combination 1 and 0, I think, for the same reasons that we discussed.
Yeah. Other interesting cases. What about? Oh, sorry. You said 1 and 1, 0 and 0.
1 and 1, 0, 1, 1, 0, and probably 0, 0 as well.
Let's imagine for a moment that we are dealing with the language where everything is sequentially consistent when all the behaviors are explained by some interleaving of these threads, right?
Yeah.
Let's imagine that. If we do this kind of reasoning, we would say that, look, there are the last statements in each of those threads, which means that one of those statements would be the last in this total order of everything that happened in the program, which means that inevitably it will read 1 because the write will happen before it, right? Mm-hmm. So we would think naively that the case that we read 0 here and we read 0 here is impossible.
Yeah, that would be a weird case.
But we do not have the language where everything is sequentially consistent. These are non-volatile variables. So is this result possible?
Well, I bet yes.
Yeah, there you go. Violate sequential consistency. And the thing is, even if we do this with acquire and release things here, if we do this with volatiles, then it would be gone because volatiles are now sequentially consistent. Mm-hmm. All operations over x and y are in total order, and the same argument applies, right? That one of the statements should be last, so at least one of them should read 1. So 0, 0 is not possible, right? Let me just run it here. But also, if you do something like acquire and releases here, right? You do release and acquire, you will realize that the power of these releases and acquires is not enough to provide you with this property. Because acquire and releases are not doing the total order. They are only about the partial orders. Something happened in one thread, we just partially move that state to all other readers of that variable, and vice versa. You don't have any sort of consensus between these two threads about these values of x and y, right? So yeah, indeed, for volatile decker, this is forbidden, and this would not be enough. Right? If you want to have the consensus between the threads about the state of multiple variables, you have to have something stronger, and this is where volatile mode or sequential consistent mode comes in. And there are two things about this consensus thingy. There are kind of two schools of thoughts about this. First school of thought says, well, consensus is really good because it's extremely useful to think about correctness. If you go to lincheck, for instance, it basically says that, it basically checks this kind of property, right? That you have the linearizable history of things, and all of these histories are fine. And it's useful, and it's easy to program to, because at least in Java, you just sprinkle enough volatiles around your programs. All critical accesses at some point will become volatile, which means they will be hooked in the total order of all volatile writes, which means your program becomes data race free, which means everything would become sequentially consistent. And it's extremely easy to argue about the behavior of this program. And there's the other school of thought, which says consensus is bad. And it's bad because if you're dealing with the distributed system, the cost that you have to go for to maintain this kind of illusion in the otherwise asynchronous world is really, really, really high. So many distributed systems basically relinquish this property and say, well, we only have like release acquire kind of consistency. Don't ask us about the global state of our distributed system there. And even on the shared multiprocessor systems, where you have only a single node, relaxing the sequential consistency of this consensus property is something that gives you performance, because even if you don't do this kind of coordination in your code, something has to do it. So hardware will still have to pay for it. Sometimes unnecessarily. If you can prove that your algorithm works without consensus, that's probably the headway for better performance there. All right.
Yeah, Aleksey, I'm sorry. That's a very good point to ask some of the questions from the chat, because they are related to the performance, if you don't mind. Yeah, so I'll join two questions because they, for me at least, they're more or less similar. Why is it rearranging the execution orders of statements allowed for more performance? If it's so rarely applied, at least in your tests. Yeah, that was about the, I think, causality.
Okay. Yes. Right. If you want to reproduce it in the single smaller test, you have to go to extraordinary lengths to actually demonstrate that it is possible. But if you actually compile a large program when you have lots of accesses, compilers are stupid machines which operate by rules. They need mechanical rules, what transformations are available or not, and what are plausible or not. And you will have, and compiler will do transformations that are allowed in the course of other optimizations in the larger code. So even though you cannot easily reproduce things in the smaller cases, in your larger cases, it would be reproduced and result in the weird bugs if you don't plan for it. In the second part of the talk, we would have one example where it reproduces in a funny way. All right?
Mm-hmm. Gotcha. Yeah, and another question about real performance. Can I have a significant performance boost if I use the trick with publishing non-volatile writes by writing a single volatile in the end, maybe with 5, 50, 100 fields, or I just or is it just not worth to risk and I should make it all volatile?
Oh yes, yeah, it is. It is a common optimization technique. When you say, look, I know that I have to carry these 5 fields to other threads. So I do the plain stores to those fields. Then I do a single releasing store, which is a volatile store. And then I do the single volatile acquire on the other side. And then I unpack this thing. So this here is absolutely common. So X, Y, and Z are non-volatile. If you read high performance concurrency code, you can basically even see the comments when you say, okay, we do this thing and that thing and that thing, and here's our releasing store, which kind of wraps everything up and kind of publishes it safely to other people. Yeah, doing everything volatile is probably not that good idea, because you would probably have more synchronizations that you need to. Yeah, but yeah, I think that answers the question. Yeah.
Yeah. Is it if we recall your idea about green zone, yellow zone, and red zone, which zone would be good for this type of optimizations?
Well, I mean, if you're not sure, make everything volatile. That's my usual thing. It's better to be slow than be incorrect. Then, yeah, relaxing some of the volatile operations, knowing that there are adjacent operations that kind of carry the state is fine. It's like the yellow zone optimization there. Yeah.
Okay, gotcha. And yeah, the last question probably from my side. Could you go back to the release acquire slide? So if we use var handler over here with really release and acquire access, would it work?
Yeah, it would work. It's called release and acquire mode because it's destined to do exactly in this scenario. And acquire release mode does not give you consensus, which in this example you don't need. You only need this publication thing.
Okay, so for safe publication, that's safe to use release acquire thing. It probably would be even more readable.
Maybe, yeah. But it's kind of it works very well when it's kind of one-sided publication. If those two threads have to coordinate, that means we will probably have to have consensus, and their reasoning in acquire and releases becomes very problematic. But yeah, if you have something like queues, for instance, it's a common thing to do. Relaxing SC is a common thing to do. Okay.
Gotcha. Thanks.
All right. And finally, we have finals. Finals are really, really special because they are able to hide the data races. They are kind of defense and depth strategy for concurrent code. It did not really fit into the whole thing there. I will briefly show you the example that you can then run yourself there, because we are running out of time in the part one. So if we say have this my object O with 4 fields, and we initialize them in the constructor there, and then we publish that object O here through the race, right? There's no synchronization on O. We store it here, we read it here, and we read all the fields. If you ask yourself whether you are allowed to see initial values in either of these fields, for this example, when this field is not volatile, the answer is yes. You can. Memory model explicitly allows it, which, by the way, means that if you write in the Java doc for my object that this class is not thread safe and it requires synchronization, and some user just ignores it and publishes it without any synchronizations, then your internal invariance is out of the window. That's bad, right? Especially if you want to run secure code. So this is where finals comes in. If you do the same thing, but you turn this thing final, at that point, you can only see here, you can only see the values of x's that are written in this constructor. And you can actually see that in the examples. And we will be seeing those examples in the next part. Okay.
Okay.
Questions?
Yeah. So, Aleksey, the question from my side. So, you prepare great content, and probably you know where is the middle. So, and the question is, how far away from the middle? So we finished the first part itself.
Part one, yeah. We could go into the depth in the other examples. We skipped benign races, I think, but we will revisit them a bit later, I think. But here we are. We are at the coffee break here.
Okay, so If you're approximately in the middle, so I think, yes, it's a good time to go to some coffee break. And one more thing from my side before we go to break is
sorry.
Yeah.
Sorry, or we may go for the benign races if you want. I mean, or
how many time is much say? So it's up to you, Aleksey. Okay, if it's up to you. If you're okay to do a break a bit shorter, that's okay.
Right.
Okay, 5 more minutes and go to break, correct?
Yeah.
Thank you. Okay.
So benign races are kind of interesting. I showed you in the very first example that data race behavior is kind of defined. So it provides you with the ability to make that thing useful for you. See here, this is a canonical form of what's called a benign race. If you have the shared variable v, you can initialize it racely like this. You can read it once racely, check that it's if it's null. If it's null, that you compute something, compute some canonical value for it, and you store it into v, and you return this the variable. Oh, damn, sorry, this should be LV compute and store to V. Yeah, or if you have read something not null, you can just return this LV, and you are guaranteed by the safe construction rules, by the rules that govern the behavior of final variables, that you will see all the contents of V, provided that all the fields are final in V, right? And it's very commonly used. For example, if you go to the abstract map in the Java util, you will see that key set and value sets are constructed as these views. You would not like to make key set volatile here because the calls to key set would cost you more at that point. But you can do this kind of benign race here. It's benign because even if there is a race you read, even if you read something through the race from here, it is guaranteed that you will read something safely from that instance because it was covered by finals. Or you initialize it right here and you publish it to others through the race, but that would be fine if that key set has only the fields governed by finals. Yeah. That's it, and this is why the last column here is resilience. Finals are kind of special in this regard. No other synchronization mechanism applied to that to fields themselves provided with this kind of guarantee. Finals do. So use them to do defense in depth thing there. So summing up this whole section, even if you don't understand the JMM as stated, you have to just remember 2 rules. Safe publications means store everything, then do the releasing store. In the other thread, do acquire, then read anything that you wanted to pass between the threads. It has to happen on all possible execution paths, and if it does, then you are fine. Safe construction, when in doubt, make all fields final, makes everything resilient to races, etc. Defense in depth, usually a good thing to provide more safety for your code. Benign races, if your object is safely constructed, you can publish it through the race if you do this right. It's the exotic optimization technique, but sometimes needed. It's probably the only easy way to avoid synchronizations in JMM without breaking lots of programs. And exotic modes, just don't until you really, really need them. All right, and this concludes part 1.
Okay, Aleksey, thank you very much. I want to add a couple of things for our audience. The first one is that we have no discussion zone during this break because we will have discussion zone after the second part of the workshop. Thank you very much that you answer really, really interesting questions. We can ask some of them after the break, or if you decide to miss it, ask them these questions during the discussion zone. And now we are leaving for a break, and we'll be back on the air at 8:20 Moscow time. It's Hydra 2021 workshop by Aleksey Shipilev and stay tuned.
Yep.
Thanks.
Со света